and let's continue from the point at which we stopped in my last class. So my today's topic is the continuation of the discussion on mean value theorem. And probably you can recall the theorem which I stated in my last class, uh, the theorem which was known as interior extremum theorem. So let us write this statement once again. Interior extremum theorem, and it says that let C be an interior point. If C is an interior point of the interval I, of interval I, at which the function f from I to R has a relative extremum, has a relative extremum then if f dash at C exists, then f dash C is equal to 0. That means at that point you are going to get, if the curve is like this or the curve is like that, you are going to get a tangent parallel to x-axis. Okay, so this is say fc and this is say f of c prime, whatever. So that is called the interior extremum theorem, and this theorem has a corollary. This corollary is also very important. This corollary is also very important, and it goes like this. Let f colon I to R be continuous on an interval I, and suppose that f has a relative extremum, f has a relative extremum at an interior point C of I, then either sorry, I lost my whiteboard. It's actually because of the internet connection. So what I wrote the corollary as let f and I, let f colon I to R be continuous on an interval I, be continuous on an interval I, on an interval I, and suppose that f has a relative extremum at an interior point C of I,
I.
then either the derivative of f, the derivative of f at C does not exist, does not exist, or it is equal to 0. It is equal to 0. So you see, this theorem, this corollary of the interior extremum theorem is actually a bit different from the interior extremum theorem, in the sense that in this corollary they have put one extra condition, which is called the continuity of the function. So in the interior extremum theorem, which the statement of which you have with you already, there they have not mentioned anything about the continuity of the function. So they have here in this corollary, they have imposed the extra condition, that is whether the function is continuous or not. Okay, so f colon I to r, this function, if it is continuous on an interval I, and if f has relative extremum, if f has relative extremum at an interior point C, then it says that this line is very important. Either the derivative will not exist or it is equal to 0. So we have already seen one example in my last class where I told you such a scenario by drawing the curve of fx equal to mod x. Fx equal to mod x, where if I draw this very roughly, I'm drawing, and this is, you know, this is x equal to 0 point, and this is the curve of fx equal to mod x, then, and we are considering the domain from -1 to +1, say. Okay, now you see this x equal to 0, this point is definitely an interior point of the domain. Okay, so x equal to 0 is the interior point of the domain, interior point of the domain, but derivative at x equal to 0 will not exist, and all of us know this. Okay, so this is one instance which I already discussed. So it goes with the corollary of the theorem. And if I draw another function, say fx equal to x square, from x equal to x taken from -1 to +1, in this case you will see that the curve will be like this. If x equal to 0 is this point, then you already know that the curve will be like this. Okay, and you know that let me put the domain over here. -1 is this and +1 is that. Now you know that in this scenario, in this case, in this case, x equal to 0 is also an interior point, is also an interior point of -1 and +1, is also an interior point of -1 and +1. I hope that you have written I hope that you have written what I drew in the previous figure. So I'm just continuing from the drawing of the function fx equal to x square. So since today some network, a bit network trouble is there, so you have to be bit quick about the drawing, because otherwise uh, I am losing my whiteboard every time it disconnects. So this is your x equal to 0, and this is the curve of fx equal to x square, and I am putting the domain from -1 to +1. Okay, and you see that in this particular case x equal to 0 is also an interior point, of the domain -1 and 1. Okay, what is f dash x? F dash x is what? Twice x. Okay, and since 0 is the interior point, so we see automatically that f dash 0 is equal to 0. So here if you try to correlate this particular statement with the this particular problem with the corollary of the interior extremum theorem, you will see that the interior point is C, the interior point C is 0 over here, and f dash C equal to 0. Okay, but in case of fx equal to mod x, I'm again drawing for the clarity because I lost my previous whiteboard. So in this particular case, it would be nice if the two examples are remain in front of you for when you study it later. So here also the situation is same, except the form of the function x equal to 0 remains fx x equal to 0 remains as interior point of the domain, but f dash 0 does not exist, and yesterday I told that this function is also very important from the sense that it says that it is a continuous function but it is not differentiable. So every continuous function is not differentiable. So these are the two cases of the corollary. So therefore the corollary is important. So corollary is saying that if you can here the function, you see here the function is defined from -1 to 1, -1 1 to r, and here also the function is defined from -1 1 to r. Okay, so in both the cases you see that the corollary of the statement is being satisfied. So this corollary is also very important. So why this interior extremum theorem is actually helpful? It's because it gives you whether sometimes it helps us to find the the maxima and minima of the function very quickly and very easily. But every time interior extremum theorem is not helpful. Sometimes we need to go to some other, we need to have some other criteria for checking the extremum characteristics of the function of some other function. Okay, so this is the starting point, I must say. Okay, this is the starting point. Now one more thing I would like to discuss is that suppose, and you must know this, suppose let us draw this figure. I'm drawing a figure like this. So suppose this is x equal to 0 and this point is x equal to 1. Okay, and I'm drawing a straight line kind of thing like this up to this, just a straight line like this. And okay, now this function is what function have I drawn? I have drawn a function fx equal to x. I have drawn a function fx equal to x, not the entire function I have drawn. I've drawn a part of it, and here the domain has been selected as 0 1. Domain has been selected is 0 1, and you see that the endpoints x equal to 0 and x equal to 1 are respectively the points of relative minimum and relative maximum, are the points of relative minimum and relative maximum. Okay, and but in neither of this point, neither of these points are zeros of the derivative. What does it mean? If you can recall that if fx is a function, and if we have a point c such that f dash c is equal to 0, then c is called the zero of the derivative. Here it is not happening. Here the function is like that. You are not going to get any tangent which is parallel to x-axis at the points, at this point and that point, although they are actually points of relative extremum and relative no, not that point, sorry, my at this point and at that point you are not going to have any kind of tangent to the, I mean, this is the day this is one of the days uh, like I actually suffered from network connection. So it is one of those days. So what did I say? I forgot my whiteboard once again. I said, yes. Now you see the zero of the derivative. So when I drew the function, fx equal to x, like this, from 0 to 1, okay, so at these points, fx equal to x at from in the domain of 0 to 1, we found that x equal to 0 is the point of relative minimum and x equal to 1 is the point of relative maximum, but at neither of these points the tangent is parallel to x-axis. But you see here x, the domain of x is 0 and 1, okay, and 0 and 1, these are the endpoints. Of the domain. Now the relative extremum theorem or relative extremum theorem or its corollary, which you have studied a few minutes ago, they actually holds for interior point only. They do not hold for any other point except interior point. So you may be asked, a student of mathematics may be asked that is interior extremum point is I mean satisfies for all the points lying in the interval. The answer is no, it's not being satisfied for the end points of the interval. So only this holds for the interior points. Okay, so now as you have understood this particular thing, so let me give you two more theorems. First of all, let us discuss about maximum minimum theorem. Maximum minimum theorem. What is that? Let I is an interval, is a closed interval with lower bound as a and upper bound as b, be a closed bounded interval. And you know what is the meaning of bounded, because A interval is bounded if it has an upper bound and a lower bound. And I asked you to go through the chapter of real numbers as prerequisites before you come into this section. So probably you have studied about supremum and infimum also. I hope so. So let I be a closed bounded interval, and let f colon I to R be continuous, on I, then f has an absolute maximum and an absolute minimum on I. Okay, so before we go to study the Rolex theorem and mean value theorem, I have to talk a little bit about absolute maximum and absolute minimum. Okay, because you have to understood this. You have to understand the difference between the relative maximum and absolute maximum, relative minimum and absolute minimum. So these concepts are also very important. Next semester, when you will be studying probability theory, you will come across a graph like this, a very well known graph, and probably some people already know this particular graph, because probably this graph is often seen in television and newspapers, and it is often discussed. My diagram is not quite okay because I'm doing it freehand, so actually I not let me draw it in a proper way. So it is starting like this and this and this and this and like this. Okay, and this particular axis is stretching from minus infinity to plus infinity, and this curve is defined by the function fx. Now the form of the function goes like this. It is like 1 by root 2 pi e to the power minus half x square, and x is lying between minus infinity to plus infinity. So for this function's curve has been drawn above. Now in this function you see that only one maximum point occurs, and this maximum point occurs at x equal to 0. Okay, and that means this x equal to 0 is the interior point of the function, and at this point easily you can see from the diagram that a tangent parallel to x-axis exists. Okay, so obviously f dash 0 equal to 0, but this is the only peak the function is having. No other peaks of the function is available. Only one peak is available, that is called it's the called highest peak, or this is called the highest frequency. So such a function, when we talk about the maximum value or minimum value of such a function, we call such a maximum and such a minimum as absolute maximum or absolute minimum. Say for example, this function is having absolute maximum at the point x equal to 0. Okay, but what about relative maximum and relative minimum? So in case of relative minimum and relative maximum, the situation is something different. It is like, suppose I'm drawing a figure like this, and suppose a curve is like this. Okay, so for example, it would be nice if I draw a known curve like this and this and this and this, like this curve, sine function, cos function curves I'm talking about. So what is that? If you talk about the interval from 0 to pi, then pi to twice pi, then twice pi to thrice pi, like this, if you do like that, so in this interval this has relative maximum, in this interval this has a minimum, in this interval this is a maximum, like this. So this maximum minimum are occurring in every interval. So therefore such maximum and such minimums are called absolute relative maximum or relative minimum. So this curve is actually different from that curve. That curve has only one peak. This curve has several peaks. So therefore that is the difference between absolute maximum and relative maximum. So similarly you can think of a function which will have absolute minimum. Okay, you can try to find out such a function if you want. And since I have actually shown you this particular function, this particular curve and the function, corresponding function, so just for the sake of your knowledge, it would be nice if I um, write the name of the function. It is called normal function, or the curve is known as normal curve. Sometimes people call it as normal curve, or sometimes people call it as Gaussian curve. Gaussian curve. Okay. So this thing is related to probability theory. Probability theory. We shall study the nature of such function in details next semester. The teacher who will be taking the class, he will teach you, or if I get chance of taking the class with CSE, then I can also take this particular. It's depends on what happens in future. Okay, so that is the thing. That is the difference between absolute maximum and relative maximum. So now let us come to the main part of our syllabus, that is called Rolex theorem. Some people call it as Rolle's theorem, some people call it as Rolex theorem. So actually it is not Rolle's theorem, it is called Rolex theorem. Okay, so the statement, and it is important also. So theorem goes like this: suppose that f is continuous on a closed interval, continuous on a closed interval, I is the interval AB with lower limit a and upper limit b, that the derivative f dash exists at every point of at every point of the open interval AB, and fa is equal to fb is equal to 0, then there exists at least one point C, at least one point C in AB, such that f dash C is equal to 0, That is the statement of the Rolex theorem. I have enabled the chat box so that you can put your attendance. Quickly you put your attendance. Now, sometimes in the examination, if you ask me that whether in the examination Rolex theorem statement is asked, the answer is yes. Rolex theorem statement is asked in the examination. If you talk about competitive examinations, there the statement of the theorems, part of the statement of the theorems are put as MCQs. Like they may make you confused about the statements. Derivative exists at some point. Okay, they may put like this: derivative exists at some point. Is it true or false? Derivative exists in the closed interval. True or false? function is continuous in the open interval, true or false, like this. So in this manner they can make you confused. So therefore this particular theorem is very important. And you see, and previously what happened, nowadays we have softwares, mathematical softwares, to study a function, the nature of the curve, etc., etc. But previously what happened, that the people in Newtonian time, the people didn't have any function. I mean, sorry, they had function, they didn't have any software, they didn't know about computers. Okay, so actually they dealt with complicated functions, and they tried to draw the graph of the function, and uh, tried to point out at the maximum and minimum value of the function. So from by studying various sorts of functions, they have come to this particular point. The thing which is being in front of you as Rolex theorem, it's a kind of a kind of cooked product which has been placed in front of you. But try to imagine that suppose you do not know about Rolex theorem, and if I ask you to study the maxima minima of a particular curve, and you do not know about Rolex theorem, and you do not know anything about uh, I have stopped giving you access of any kind of internet, and you are closed and confined in a domain where no internet is available, no book is available. So only you have pen and paper, and you are going to analyze different sorts of functions. So in that kind of primitive stage, you will feel the blunt of finding, I mean, finding kind of a theorem which will be true for any function, satisfying certain properties. So these properties which they have given over here, behind it a tremendous amount of uh, I mean, hard work is there. So you have to feel it. That much hard after that much hard work, the a particular mathematician was able to put a kind of cooked product like this Rolex theorem or mean value theorem, so any theorem or interior extremum theorem, so that it helps you in studying. It helps you further in studying the extremity of the functions, various functions. Okay, geometrical interpretation of Rolle's theorem is very important, and it is shown in the uh, book. So although I'm trying to draw it over here, so it is very simple. It says that suppose we have 2 points like this, and suppose we have a graph like this. Okay, we are considering a graph within this interval. The graph is continuous. Okay, and derivative exists everywhere, including the points A and B. Then what will happen? At this point, you see here the function has relative minimum. Here the function has relative maximum. So therefore the word at least 1 point, at least one, that is one or more than that, that has been mentioned over here. At least one. Okay, so at least one means one or more than that. So you are getting 2 points where relative minimum, relative maximum is existing. And also you see that derivative of the function will occur at the open interval AB. So the criteria has been actually was that it's kind of, I mean, it's a kind of a weak criteria, that they are not talking about the existence of the derivative at the endpoints. Okay, doesn't matter for the existence of relative maximum, relative minimum. It doesn't matter whether the derivative exists at the endpoint or not. But if the derivative can exist in between, and the function is continuous over here, then at least 1 point you are going to get where the function uh, I mean, the function's derivative at that points, at those points, equal to 0. And fa equal to fb equal to 0 means this is the fa value. It is 0. You see, it is falling on the x-axis, and FB is falling on the y-axis, x-axis. Both these values are 0 over here. So this particular function, this particular curve actually satisfies the criteria, the characteristics of Rolex theorem, and therefore we can get two extremities, this and this, that is f of c prime and that is f of c. This is c and that is c prime. Okay, this much for this session 1. I'm pausing the recording, and the next session I'm going to continue with the discussion.